So let's continue further. So cross product length. Now that we know the direction of A cross B, the remaining thing we need to complete is its geometric description is its length A across B, and then this absolute value sign, or just the length of it. Or in other words, how long is this vector? What's the magnitude of that length? So this is given by the following theorem. This is theorem 2. So if theta is the angle between A and B, so that theta is less than pi, or 180 degrees, or pi radians, and greater than or equal to 0, so less than or equal to pi and greater than or equal to 0, then the absolute value of the magnitude, or the length of A cross B, the absolute value sign, equals 2 absolute value of A times by absolute value of B, and then over the length of A and length of B, times by sine of theta, like that. Alright, and now let's take a look at the proof of this theorem 2, and the proof is quite extensive, just very tedious, but pretty straightforward. So let's just jump right in. So from the definitions of the cross product and length of a vector, as in my earlier video, just basically the distance length formula. Yeah, so what we have now is, let's just write this down. So what I'm going to do is I'm going to take the square root of this cross product vector, and then define it using the length of the vector formula. So that's going to be right here. So the length of the A cross B, then square it, just so we're dealing with squares, is equal to, again, just Pythagoras theorem, essentially in 3 dimensions. So this is going to be, so this vector is going to be C. I just write it like here. This equals to, remember this one, this is going to be C1 term squared, the x term squared, and then the y, then the z. This is going to be C2 squared plus C3 squared, like that. And then to get the distance, you would square root everything and get rid of this. But anyway, so that's what we have there. And we know what these C1, C2, and C3 are. Those are just using the cross product. And that's going to be the C1 is going to be, well, it's going to be our A2, A3, if you remember that. And then it's going to be A3, this is A B2. A2, A B3, and then A3, B2. And then we're going to square this. And remember, this is the, that's just going to be right over here. This is A cross B. You have the first terms A2, B3 minus A3, B2. In other words, this part right here. And yes, we just have this here. A2, A3 minus A3, A2. And then the next one's going to be negative A1. Negative bracket A1, A3 minus A3, A1, and so on. All right, let's just continue back here. And, but here again, we're going to be squaring it, so it doesn't really change anything. Yeah, so whether you put plus or minus, it's going to get rid of it. But I'm going to do is I'm going to put a plus here, and then put this inside. Remember, it's going to be our negative A1, B3, but I'm going to switch it all up, and just write this as A3, B1 minus A1, B3. Again, just multiply that negative inside. Same thing as here. So negative inside here. So negative, we'll have this positive A3, B1 minus A1, B3 once you get rid of this negative there. But anyways, it doesn't change much because you're squaring it. So we have squared like that. All right, so now the next one is the C3, and that's, remember that, this is going to be their A1, B2, and then minus, this is going to be A2, B1, and then square this again. And now we're just going to FOIL out or expand all of these squares. So let's do the first one here. So this term is going to be multiplied by itself, then multiplied by this one. So in other words, we're going to have an A2 squared, B3 squared, and then minus here, and let's write these all in order. So A2, A3, and then we'll have a B2, B3. Like that, put this all in order. The next one's going to be this multiplied by this, and then itself. In other words, we're going to have the exact same setup as this. And so in other words, we just add them up, so we'll have a negative. We just added 2 there. It'll be 2 of those, and then this one multiplied by itself. The negative becomes positive. This will be a plus A3 squared B2 squared. And now the next one, I'm going to put this, we're going to FOIL out the middle one, but I'm going to write this underneath just so it's all in one stacked up column. It's easy to simplify. So just write this out. So just multiply by this, and then multiply by that. In other words, we get plus a3 squared b1 squared minus, now we're going to have a1, a3, and then b1, b3. And then next setup is this multiplied by this and itself. In other words, we're going to have the exact same this, add a 2. And then plus, the negatives cancel, a1 squared, b3 squared. And now the next one is, we're going to go over here. This times this, and this times this. This is going to be, this is going to be a1 squared, then b2 squared, and the next one, these multiply each other. Just write these all in order. a1, a2, b1, b2. And now the next setup is this multiplied by this, and then this multiplied by itself. In other words, we're going to get the same one here. Put a 2, and then plus right here. This the negatives cancel. So a2 squared, and then b1 squared, like that. Yeah, so now we have two very interesting setups. One of them is these square terms, and the other one is these -2 terms like that. So what I'm going to do is I'm going to separate all of them and write these in order where the A1, A1 to A3 and B1 to B3, etc. So the smallest one we have is this A1 the A1 is the smallest one there. So A1 squared, B2 squared, like that. Now the next one's going to be, well, the next setup always use the A1 as the smallest, basically go from small number to big number. So A1, B3. Just write this in order just to find a pattern. A1 squared, B3 squared. And the next one, there's no more ones. We'll look at the 2. So the 2 is this one right here. And that is, well, just plus A2 squared, B1 squared. And the next 2 is over here. A2 with 3, B3 there. Plus A2 squared, B3 squared. And the next one is just A3B1, A3B2. Plus A3 squared, B1 squared. And then plus A3 squared, B2 squared, like that. Alright, so now that we have that, and I'm going to do this here. I'm going to factor out the negative, but keep the 2's there, because they're very interesting. So we're going to have a negative, and then keep them all there, make it from the smallest to biggest, so A1, A2. Alright, so I have a 2, A1, A2, get rid of all these lines. Whoops. This line, this line, this line. So we'll get this one first. A1, A2, B1, B2. And then the next one's going to be plus this one right here, A1, A3. A1, A3, B1, B3. And then the next one is this one right here. And then just get rid of all these. This is going to be plus 2, A2, A3, B2, B3. And now we could find some interesting patterns. And now the interesting patterns here is not what's shown, but it's what is not shown. And this is pretty next level proof here. And what we'll do is, if you take a look at this one right here and the bottom one, this part right here in the bottom, there's some cancellation going on when we take a look at this. So I'm going to write here first. Note what happens when we have this kind. So we have this A1, B2, but there's no A1 or B1. There's no A3, B3, etc. or A2, B2, and those ones. That's because they would cancel when we write them in a way that we're going to show right now. But first, I'm going to do is note that when we have this setup here, let's say we had an A1 squared plus a B1 squared, just so we have all these multiplications. So A1 squared, B2 squared, and so on. So if we have A1 squared plus A1 plus A2 squared. And then the next one plus A3 squared. And then multiply this out by B1 squared plus B2 squared plus B3 squared. This equals 2. Yeah, so this whole thing equals 2. And I'll write this actually. Let's make it some neater here. Move it here. And write this as this equals 2. This is B3 squared. So again, FOIL this out. A1 goes over here and A1 goes across like that. This is going to be, the top's going to be A1 squared, B1 squared. Notice that there's no more A1 or B1 squared. I'm going to circle the ones that are not inside this setup here. And the ones not inside is this one here. There's no, with the same numbers, a1 and b1. The next one's going to be this multiplied by this over here, b2 squared. So a1 squared, b2 squared. And that is this right here. So we have that, but we don't have this one here. And the next one's going to be multiplied out. It's going to be a1 squared, b3 squared. So we have all the ones where we have b3. It's not a cube, it's squared. And then what you'll see is this right here. Yeah, this one right here shows up here. So all the ones that don't have the same subscript are showing up there. Now we'll do the next setup. Next setup is this right here. This multiplied by this, and then this. So the first one's going to be plus a1, a2 b1 squared, a2 squared, b2 squared, and then the next one's going to be the same subscript. So a2 b2, a2 b2, and yeah, this one's a2 b1, not b2, and then the next one's going to be a2 squared, b3 squared multiplied by this one. And notice again, this a2 squared b1 shows up here. This one here, a2 squared b3, shows up here. So they all show up, but the ones that don't is the one that subscript's the same. So I'm going to circle this right here. I'm going to circle that. This one and this one aren't there. a2 squared, b2 squared do not show up in this top row. And let's do one more, is multiply this by this, and add them up. This equals 2 plus, we'll have an a3 squared, b1 squared, and then plus, and you can see the pattern. Very interesting. A3 squared, b2 squared, and the next one is a3 squared, b3 squared. Again, these ones show up a3 b1, a3 b1, a3 b1, a3 b2, a3 b2. So those all show up. This one a2 b3 is over here, and so on. a2 b1 here and here, and again, I just did double check that. And then lastly, there is no a3 b3 inside there. I'm going to put a plus here, and I'm going to circle the ones that are not inside. Alright, so now that we have this, this is pretty much this entire thing, but there's these extra terms. And now we have this part right here. So notice what we have here, this 2a, a1, a2, b1, b2. And these ones arise, remember when you have these squared, when you're multiplying the ones that are not itself, you're going to eventually have this 2 there. So this gives us the idea of, well, let's just try to square these ones all together. So we'll have this a1, b1, and then a2, and then plus a2, b2, plus a3, b3 all squared. Yeah, in other words, so first note that, and again, this is why this proof is a bit next level. We'll take, if I didn't have the solution, well, then even the solution, the calculus book doesn't actually explain this. They just go jump straight ahead, and I just had to, then I had to go and obviously reason that this is what they're doing. But if I had to do this from scratch, it might take a few days to figure out how they did this. But anyway, so now another thing. So we have this first, and now the next one is and. Note that to get this set up here. So what we're gonna do here is I'm gonna write a1 b1 plus a2 b2 plus a3 b3 squared. And again, the reason is when you're squaring these, when you're multiplying the not itself, you're going to eventually get something like this, where you have a1 b1, a1 b1, and then a2 b2, etc. Multiplied by there, and so on with these a3s. So when we're going to square this, so this equals to, well, this multiplied by itself, and then multiplied by this, multiplied by that. This is going to be, well, a1 squared, b1 squared. And I'm going to circle the ones not inside. And that's this one here. Remember, this matches up. That matches up, and it's not inside this part right here. Next setup is a1 and then a2, b2. So we're going to write these in order, a1, a2, and then we'll have a b1, b2. Let's put these in order just so it matches up with this. So we have this part right here. That's one of them. Next setup is this is going to multiply by this a3 plus a1, a3, b1, b3. Yeah, A1, B1. Yeah, so then, and that's going to match up with this right here. A1, A3, B1, B3. One of them, not two of them. But then we're going to get that eventually. So now we're going to multiply this by it, this one, by itself, and then by this one. So it's going to be plus A1, A2, B1, B2. And that's going to be the same as this one. You're going to add these up. It's going to be 2. Those add up and so on. So we'll do that in a bit. And then the next setup is going to be, well, this by itself is going to be A2 squared, B2 squared. So notice that. So this is not inside any of them, but it matches up with this. Next one's going to be, well, A2, A3. A2, A3, and then B2, B3. And that matches up, well, it's going to match up with a different one. That's going to be now the next setup here. But again, also notice A2, A3, B2, B3. That's right here, A2, A3, A2, A3, B2, B3. And let's do the next setup is this one, multiplied by this, then itself. So that's going to be plus A1, A3, B1, B3, which is this. So those add up to be 2 of them. And the next setup is A2, A3, and then B2, B3. So that's, again, this multiplied by this, and these ones add up to 2. Yeah, so 2 of those. These are the exact same ones. And then this multiplied by itself is going to be plus A3, B3, squared, squared. So this is not anywhere inside here, but it shows up here. So then, in other words, all these terms, yeah, all these terms are inside here except these ones, and these ones actually can cancel. But let's just add these up. So this adds up with this with this, and this with this. So this equals 2. This equals to 2 A1, A2, B1, B2 plus this one right here, 2 A1, A3, B1, B3 plus 2, and then this right here, A2, A3, B2, B3. And then likewise, we'll just add these up there. And then over here, it's going to be A1 squared, B1 squared, plus A2 squared, plus B2 squared, plus A3 squared, B3 squared. So in other words, we have this part right here, and this part is when we combine these two, but then these all cancel. So thus, I'll put these all together. Thus, we get, and let's write this all down, thus A cross B squared is equal to, let's go A cross B is equal to, well, this is a C squared, like that. Yeah, I forgot to add that square there, but anyways, we have a square there. Everything's squared. This becomes C squared, like that. And this equals 2, and it's going to be, what I'm going to write down is this part right here. So this is A1. Yeah, I'll write these all out. I'm going to write this out like this. A1, A2, yeah, so let's write these out. A1 squared plus A2 squared plus A3 squared times by B1 squared plus B2 squared plus B3 squared minus this one here. So now it's going to do minus, and it's going to be minus, but actually to save some space, I'm going to remove the C squared, but a good thing we caught that that mistake. We had forgot the square, and then it's going to be minus, and then this part right here, all squared. Let's get rid of this thingy. Minus A1, B1 plus A2, B2 plus A3, B3 squared. Because remember, so when you have this minus this one, all of these cancel. And we're just going to be left with this giant -2, etc. there, which is just this whole setup here. And all of these extra terms. And then these ones are all gone. So these just all cancel, which is quite fascinating. All right, so that's what we have there. That's what this equals. And now, well, let's shift this over. Get some more room. like this. And now, well, what do we have here? This right here is equal to, this is just the distance formula squared of a1, of a vector squared, like that. Yeah, that's just distance formula, or the length of it. Remember, a1 squared plus plus a2 squared plus a3 squared. So those are all the ones, you just square them, similar to the c1 to c1 squared plus c2 squared, etc. So you all those up, and then this one here is the b vector distance squared, or the length there. And now this part right here, inside here, this is just a dot product. Inside this thing is just a1, b1, all the terms, and add them up. In other words, this is just a dot b, like that. So what we get is, well, this whole thing is equal to, let's put an arrow, so I'll just leave it like that. This equals to a vector, the distance vector, a squared, and then like this, b like this, squared, then minus, then this is all squared, 2, so of an a dot b vectors, yeah, dot product squared, like that. Like that. And now if you recall the dot product from our earlier video, this dot product is equal to, this one is just equal to, well, a vector, the distance of a, so the length of a, times length of b, and then cosine theta. That's just a dot product there, in with a trig format there, or the geometric interpretation or definition. And then this just then write this whole setup, and now you're squaring it. So this equals, let's put an arrow like that, or just leave the arrow so that it equals that. So now this equals to a length of a squared times length of b vector squared minus, and then this is all squared, so we're gonna have to square everything. A squared length, a length of a squared, length of b squared, and then cosine squared theta. And now what we could do is, well, factor out this a squared b squared length. This becomes a squared b squared, then factor that out, becomes 1 minus cosine squared theta. And again, recall the Pythagorean trigonometric identity. Recall that you have 1 equals to sine squared theta plus cosine squared theta. So in other words, move this over to this side, you're going to get this sine squared. So 1 minus cosine squared theta equals to sine squared theta. So this whole setup equals to, and I'll put this all here. So we'll have, a cross b squared is equal to a length of a squared times length of b squared, and then we're going to have, here, sine squared theta, like that. And now we're going to recall the sine function. So we're now recall just the sine, so recall that it's positive for thetas between 0 and pi. So recall, if you have here, this is theta, this is y, like that. This is positive from pi, this is 0, and this is sine theta graph. So in other words, we have here's positive, so that means square root of sine theta, square root of sine squared, of sine squared theta is equal to sine squared, because it's going to be, so you cancel this out, and it's going to be it's just going to be equal to sine squared, because it's always positive. So because remember, when you ever have this squared there, the squared makes the sign, if it's negative or positive, makes it positive, and then the square root just becomes a sign. But this case, because it's always positive, you could just square it, and you don't need to worry about negative sign. So I'll just put sine squared equals the square root of sine squared is equal to sine squared because, and then write because sine theta is greater than or equal to 0 for, let's put the 4, I'll just shift everything over to the left, for theta is less than or equal to pi, or 180 degrees, and greater than or equal to 0. Alright, so thus we have, put it like this, and drag this out here, so thus we got square root of this whole, squared this whole thing, square root of the dot of the cross product A cross B squared equals to square root of this whole setup here. Length of A squared, length of B squared, and sine squared. Like that. This equals to, yeah, this all of this cancels, so we're going to be left with A cross B equals 2, and all these squares cancel. We're just going to be left with A length of A times length of B times sine theta. And there is our proof of Theorem 2. It's pretty extensive proof. I had to go a bit outside the box using the FOIL method of algebra FOIL method of those functions. And yeah, let's go scroll all the way back up to the theorem that we're actually proving. There it is. A cross B, the length of it equals to length of A times length of B times sine theta, for theta is between 0 and pi, or 0 and 180 degrees. All right, so now that we got the proof there, let's continue marching further. So since a vector is completely determined by its magnitude and direction, we can now say that the cross product A cross B is the vector that is perpendicular to both A and B, whose orientation is determined by the right-hand rule, and whose length is the length of A times length of B times sine theta. In fact, that is exactly how physicists right here define A cross B. Very interesting. So define it this way as opposed to mathematics. We proved it this way.